Well, good morning, afternoon, maybe evening to some of you. Welcome to this month's ESIP Open Science Cluster webinar. We've been holding these monthly webinars to kind of highlight and increase awareness around a number of open science themes. We have covered trust in open science infrastructure considerations, and then we'll have a final webinar on kind of open science incentives. Today, we're thrilled to be joined by Dr. Natasha Stavros. Natasha is the founder of Wicked Solutions. Wicked Innovation is a framework that uses system engineering, design thinking, and scientific method to mitigate risks while creating disruptive technology that changes actions. Natasha specializes in end-to-end data and information system engineering, including facilitating collaborations among interdisciplinary research and decision makers, mapping inter-organizational information systems, assessing market needs, and architecting and managing projects to fill gaps between information demand and data supply. Natasha actually developed these skills as a fire and terrestrial ecosystem ecologist, but she applies them in other complex systems with a particular emphasis on NASA flight projects, technology, and data systems. In today's webinar, which is titled Open Science Cyberinfrastructure Supports Equitable Access to NASA Big Data, I should have actually asked you ahead of time how you pronounce this, the ImgSPEC case study. Natasha will discuss how the surge in open access data really necessitates proficiency in domain science, as well as data science, as well as computer science. And mastering these sciences simultaneously can be daunting. Natasha will share the ImgSPEC case study, a NASA Advanced Information Systems Technology demonstration promoting open science cyber infrastructure for enhanced big data processing. And just a couple of notes to please complete the docs page if you get a chance, just so that we can capture who is attending the webinars, etc. Natasha, usually we encourage the presenter to give the presentation and then have Q&A at the end, or would you like questions during the presentation as well?
No, that sounds like a great approach. And hopefully it's a pretty short presentation, about 30 minutes. So there should be plenty of time for discussion and feedback. And hopefully this gets some juices flowing and people have some good conversations around it.
Perfect. Well, thanks ever so much. We can see your screen and I will go ahead and pass it over to you.
Thank you so much, Jenny. So as Jenny said, I'll be talking about open science cyber infrastructure with a focus on equitable access. But before I begin, I want to acknowledge my co-authors, Tyson Sweetnam, who's on the call, who's from Cyverse, and Hakua, Sujan Shah, Marjorie Lucas, Namrata Malarut, who are all from JPL, Justin Mers from UC Davis, Eric Verlee from CU Boulder, Michelle Gurak from JPL, and Phil Townsend from University of Wisconsin. And then I also want to acknowledge Marco Lavalle, who's at JPL, for a figure that he contributed in this presentation. So without further ado, there we go. So we are in the information age, which is defined as an era of unprecedented Earth system observations. And there have been a lot of claims that science advancement will harness data from diverse sources, of which NASA contributes a lot of open access data. You can see here that by 2025, NASA will be contributing 247 petabytes of data. And with an ever-increasing breadth of data, it's important to note that no one project or agency would have the resources to generate all of the value-added information that's useful from the data that we collect. And so with that, we have this potential opportunity to transform our understanding of Earth, but we just need to figure out how to harness that ever increasing data streams. And so some of the barriers that we know exist to using big data are lack of knowledge of data curation and munging, lack of expertise for working with or the ability to access resources capable of scaling workflows, cultural shifts to working remotely in scalable compute environments rather than on somebody's personal laptop. So that could be a high performance computer or a server in a lab. It could be on the cloud. But either way, knowing how to use and access those resources is non-trivial. And so we recognize at the same time as all these barriers, this need for analysis-ready data. And often we think of that as data cubes. So getting data sort of all pre-processed, where it's all geocoded and geo-registered. It's stacked all at the same resolution in time and space. But doing that is a very custom process depending on what it is you're trying to use that data for. And so saying that you're going to produce an analysis-ready data cube that is going to fit everybody's needs is sort of, it's a very difficult prophecy to fulfill. And so that's where this vision of data services for data wrangling, munging, and processing come into play. And this is actually kind of the basis for the GIS platforms that we have, saying that instead of trying to provide a hand-off-the-shelf data product, we're going to provide the services that enable people to get it to the point that they're able to then do analysis. And so while all this is happening, we've got a lot of data. We know there's barriers to using that data. We're thinking about how do we get it into analysis-ready data. NASA is also celebrating its year of open science. And it's defining open science as a collaborative culture enabled by technology that empowers the open sharing of data, information, and knowledge within the scientific community and the wider public to accelerate scientific research and understanding. Fantastic vision. But the next question kind of becomes, so how do we actually provide the technologies that enable open science? Knowing that NASA's got these large data volumes and knowing that we've got ever increasing access to scalable compute via commercial cloud, for example. And so in this landscape of all of these different sort of moving parts, you have to think about open science as not merely being open access. In particular, it is inclusion of culture with variable security and privacy controls that enable many to participate in the scientific process while accounting for variable value systems, means, and capabilities. So most important thing to walk away with is that equal access is not the same as equitable access. And I really like this figure that I found from the National Alliance Partnership entity, I think, NAPE, that really shows the difference between equality and equity. So if you think about, okay, we just make it equal access to the data. Everyone has equal access. Not everybody is capable of using that. Whereas when you provide variable services based on what different people need to be able to access it, you're enabling more people to participate in the process. And so this is really the theme for my talk today. And it really gets at defining open science cyber infrastructure as the hardware, the software, and people analyzing and visualizing data with explicit consideration for variation in security, accessibility, and experience that inhibit diverse groups from participating in the scientific process. And so this kind of begs the question, NASA's got this year of open science. What would a NASA open science platform look like? And for ImgSPEC, which is ImgSPEC is ImgSPEC, what we posit that it looks like is it would support analysis by diverse perspectives through inclusive collaboration that increases access to data tools, and compute resources by removing the common barriers to entry, like learning curves, steep learning curves for onboarding into different compute environments. And it would allow us to implement open science best practices such as FAIR and CARE data principles, which I will talk about more if you're not familiar. Most people in the scientific or in the computer science community know about FAIR data principles: findable, accessible, interoperable, and reproducible. CARE data principles came about in 2020, and that stands for collective benefit, authority to control, responsibility, and ethics. And I'll definitely talk about these a little bit more in the talk. So with ImgSPEC, we wanted to prototype and refine the open science use case for using diverse, different mission data sets by stress testing the bounding conditions on contributions from users outside of designated missions for on-demand product generation. So again, this idea that like, we can't produce analysis-ready data for every single scientific domain and every single application, but we can provide the services that help people to get to analysis-ready data more easily and then customize it. And so with that, we really sort of had to constrain ourselves, because it's easy to look at a big vision and want to do all parts of the vision simultaneously. But in order to actually get to something tangible, we said, look, let's start with imaging spectroscopy. It's high dimensionality spectral data. It's really big data. And it's becoming the go-to source for so many different communities. There is no one data cube that you could produce that would serve everybody. And so it's really a great little test case for us. And in order to actually use this data, you have to bring in data from the ground. You can't really, this data doesn't, it's hard to infer without calibrating it, calibrating your algorithms against things on the ground. And so it brings in this diverse data sources component. And so the problem with imaging spectroscopy data is that while it is so valuable and provides so much information to so many different groups, it's really actually quite hard to use the data, because you need specialized expertise for pre-processing that data, for knowing how to manage data of that size. And so agencies or other product developers may not actually have the capacity to generate all the value-added information. And so this inherently limits the utility of the data and inherently limits the accessibility of the data, because you've already created a barrier that says you can only use this data if you have these expertise, or if somebody has already created the product for you. And so our objective, we focused on the terrestrial ecology use case, just to say that like many different disciplines, and we needed to kind of constrain ourselves to which set of algorithms we would use to demonstrate this. But really, it's independent of the terrestrial ecology use case. It was just what we used to run through the system from end to end, with the idea that people would need to generate on-demand processing to create these higher level information products and analysis ready data products. And so that's saying, okay, level one, not quite, what we would call analysis ready. Level 3 is at least on a common grid. And so, we're getting closer to analysis ready. Let's streamline that process. And we wanted to focus on researchers' biggest pain points. So the first was we wanted to democratize development to the value-added products and analytics. In particular, this is the idea that I, as a wildlife biologist who doesn't know anything about remote sensing, want to use remote sensing data, but I don't know how to do that. And so I'm limited to only downloading information layers that USGS has pre-processed for me into something like land cover type. That puts the full burden of processing to information on the USGS. And so by democratizing development of those value-added products, we're making it possible for lots of different groups to buy in and decide what kind of products need to be developed. And to do this, we actually need to reduce barriers via seamless user experience to transition from a local computer to something that is scalable and can handle really big data. We need to reduce our download times, and we need to facilitate reproducibility. So that's actually very non-trivial, right? The number of journals that are asking for fully reproducible workflows and data with metadata and provenance and making that all open is non-trivial. It's a big lift for scientists who don't fully understand it and haven't worked it into their workflow from the start. And this is the figure from Marco that just goes to show you the power of scalable compute and why we think this is so essential in the era of big data and information age. You can see what we can produce on a single granule or a single machine. For a single granule on a single machine takes about 17 minutes. But if we were to scale that and do close to 1,000 granules to cover the entire world, we could do that in 30 minutes. It's not linear, right? And so that's why we see, like, as more and more data information becomes available, either via Internet of Things or remote sensing or any number of cameras on people's phones, et cetera, camera traps for wildlife, we need to be able to scale to process all that data. And so ImgSPEC sort of focused on creating a collaborative work environment and the interface associated with it for generating those on-demand custom products as well as standard products. So this is not an argument to say, like, oh, well, NASA can't afford to do all the products, so NASA shouldn't produce any products. No, there's still value in that because there's a gold standard, because they do full provenance, and they do make sure that their algorithms are calibrated to be globally applicable and serve 80% of the world. And be accurate for 80% of the world, right? So there is still value in that standard product generation. There's also value in on-demand custom products. And so we wanted to serve that. And to do that, we broke it up into these capabilities. And so first is the ability to deploy an analysis environment that is familiar to the user. That could be Jupyter Hub or a Jupyter Lab. It could be R Studio. We also wanted to build in the interfaces to things like NASA Earth Data Search. So instead of launching their own environment and then going to a completely separate application like their browser to load up NASA Earth Data Search and then figure out how to connect from one application to another, we thought about all those interfaces for them, and we created a plugin so they literally have in their deployed environment a drop-down menu that launches NASA Earth Data Search. We're not launching our own version of it. We're directly launching the browser, and then we've created the streamlined back access for them so they don't have to figure that part out. We also did that with NASA EcoSys, which is a spectral library, and EcoSML, which is a model library. So if you imagine sort of like algorithm search, faceted search, right? So instead of just doing data faceted search, you're doing algorithm faceted search. The ability to load their own data. This was really essential. It is currently a huge barrier to using platforms like Google Earth Engine. People need to load their own data, feel safe and secure that that data is maybe not being accessed, find and publish their algorithms and workflows publicly, or keep them in-house to themselves. They might want to use somebody else's algorithm. And you could say, well, we have GitHub, but GitHub is very hard to search. So again, having that findability of certain algorithms that are linked to specific kinds of data that you want to work with, but also having the version control functionality that GitHub has, and then finally loading open source software that is appropriate for them for doing their job. deploying algorithms as a container for scalable backend. So again, going from a script to an executable, helping them to automate that process. And then metadata curation and provenance. So again, this is non-trivial, but having a GUI that helps a user figure out what is the information I need to be providing with a data set in order to make this something that is considered compliant with fair data principles. The ImgSPEC system design actually leverages the NASA MAP platform, the multi-mission algorithm and analysis platform. So this is not in competition with MAP. This was in supplement to MAP. So this was saying MAP was originally designed for NASA and ESA to work together on their biomass missions. So it's put a lot of thought into thinking about how groups work together to validate and work with different missions data, but it's still within intranet. And so what I mean by that is ESA has its own intranet, NASA has its own intranet, and they push to each other and they've onboarded and secured, and people have gone through onboarding processes and have security badges and are able to access the system. What we wanted to do is we wanted to take that technology and we wanted to build on it and say, what if somebody wasn't in the internal system? What if they came from the outside, right? What if they came from Department of Homeland Security and they want to generate an algorithm that, hey, isn't related to biomass, but the data is still relevant for, how could they use that system? How about somebody from a university? And this is why you saw so many university partners on this. And so our main focus was simplifying the interface to make it intuitive for the user experience, streamlining APIs to make that process easy. Every time you have a new API, you have to learn that API. And so by having some software engineers who create plugins to make that API a little more easy, you're removing that barrier to entry. And of course, if somebody wants to go learn the APIs, nothing is stopping them, but it's just creating that extra step to say, hey, if someone hasn't learned it, they can still participate. And then automated scalable backend. So with this prototype, we did 6 user acceptance tests. The first 3 focused on end-to-end testing. So the first one was end-to-end testing, just connecting all of our subsystems and doing like no load testing. Just does it work end-to-end? Are there any leaks, if you will, and like a plumbing test, if you will. And then the second one was testing a default standard workflow with registered open source code. So if we were to take a data product, a level 1 data product, and we wanted to just run it through, a vetted, pre-approved atmospheric correction to create level 2, and then a regridding process to create level 3 products, can we just run that? And so that was the second test. The most important thing that we learned from the user acceptance testing with respect to that was around demonstrating job submission capabilities and checking for duplicates, checksums, and filtering. So here is where it was really like, great, okay, you can run this, but like, how do I as a user know that I'm not burdening the system, and the system is creating the fail safes to make sure that it's not being overtaxed by the user or misused by the user. The third test was around testing user customized deployment of default standard workflows with registered open source code. So this would be saying, hey, we've got a vetted atmospheric correction, but we want to calibrate that atmospheric correction with our own field station data rather than using reanalysis model products. You could customize that run. And the main feedback we got from users in that testing was that we really needed to modify the user experience by adding browse images to help them with their faceted algorithm search. So how do I know that this is a vetted algorithm, or how do I know that this algorithm is connecting to this type of data that I want to put in? And then with respect to the browse images, this is where it was feedback around, okay, well, I ran my custom workflow. How do I know it's better than the standard workflow if I were to just assume the defaults. And so that's kind of some of the feedback we got. With respect to user acceptance tests 4 and 5, they focused on adding interfaces to the eco-spectral model library and how we would deploy customized workflows. So this is really with respect to user experience for deploying auto-scale jobs via a workbook and via a GUI, or a graphical user interface, with drop-down menus, and also auto-scaling to cost. And security concerns about releasing data publicly versus keeping it within the user's environment. And so this really led to two key pieces of feedback, which was deployment with respect to costing and ownership. So you need clear delineation of who is paying for what, and specifically whether the full burden of cost rests within the intranet, i.e. like NASA or ESA, which limits the users via security and resource allocation. So NASA has to deem you worthy enough to allow you into their system, or on the individual who probably can't afford to deploy a very complicated system that has all of these automated things in them. The second had to do with benchmarking key capabilities like auto-scaling against existing infrastructure. So this had to do with the incentive structure for the user. Why would the user come use this system when they could go buy their own server and just deploy and run there? And this came back to kind of user experience, which was our 6th test. So saying that, like, yeah, they could go buy their own server, they could go deploy their own RStudio, but it's not coming with all of that extra services that help them with deployment, for assessing and setting up resource allocations, or auto scaling within the capacity of their environment, or implementing certain language and tools that may help them that they didn't know they needed, specific to their data, or variation in how they want to see the expected output. So let's say they don't really want to handle a huge image. They just want the data over their field location. These are all extra services that can help take big data and make it manageable so that more people can access and work with that data. And that might not be available to them if they were to go get a server. And so really, ImgSPEC was this prototype that gives us some key essential lessons learned. And the key conclusions of ImgSPEC, to me, with respect to open science cyber infrastructure, are that it is highly desirable. People were really receptive to this idea of a system that facilitated reproducibility and provenance. That really is a big pain for them, and for big data processing to scale. Not every lab can afford to have a software engineer help them scale their workflows. And that, the community could generate the algorithms rather than relying on an agency to deem that product worthy. But at the same time, it's not feasible as it's currently implemented. And so this really comes to the cost model, that we can't build the system that deploys by a single project, because that puts the full burden of cost to deploy that on the agency that's running it, and i.e. who can access it via security, or on the user. And so what we really need is something that's more hybrid, in order to create a sustainable business model that would not impose the same kind of constraints that we see today. So with that, open science cyber infrastructure really needs to serve across the computer science experience, security, and affiliation gradients. And so what this does is it enables all to access and use big data without presupposing their skill, ability, resources, values, or needs. And so what that looks like is, it looks like users launching and deploying their own preferred environments and languages with streamlined data access and GUIs to facilitate use of APIs, support computing resource calculations, guide them through batch processing and containerization for scalability and reproducibility, supporting FAIR principles, that then sort of necessitates the provision of federated or core services. And so this is the idea that rather than the government providing all of the generated information products, it shifts to a service model where it's provision of these services by the government and the maintenance and operation of those services by the government, rather than constantly reprocessing data into different formats and presupposing an end use. One thing I do want to call out is that when we talk about access, there are other barriers to access that I have not mentioned, and I don't have the solutions for these. But even with federated services, it assumes that people have access to broadband internet, which is not true in rural parts of the world, even within the United States. So I know that a lot of Indigenous communities live in really remote areas that don't have access to broadband internet. So if we build this system, are we still excluding those groups from participating in the scientific process? Also presupposing English language. Obviously, there are lots of other languages out there, and you could argue that, well, the United States speaks English, and so therefore our agencies are going to create their services in English, and that's fine. But I'll talk about a solution around possibly this one, ability of senses. So this is really thinking about accessibility from blind, deaf, those kinds of limitations that people or challenges that people have to overcome. And then finally, financing ability. So you say, great, okay, the user deploys and the government pays for funds. We're still presupposing that somebody has the funds to pay for that system. And I'll talk about this one again in a couple slides. So when we think about this and we say that, open science is about bringing everybody to the table to accelerate knowledge generation, what we're talking about is that it's sort of the fundamentals of science, that no hypothesis can ever be proven right. It can only be disproven. And the more different approaches and analyses from diverse perspectives that are tested, the more confidence we gain in our scientific understanding. And so the faster we can onboard more people into the process of knowledge generation through the scientific process, the more confident we can become in what we understand, and we can test new domains and push the bounds of our knowledge. Services can support equitable access to data and compute, and this can help in that process. It can enable diverse users ranging in expertise, country of origin. So NASA doesn't have to onboard people from the Middle East. The Middle East can launch their own environment, and they can just use NASA services to access NASA open data, but they're not in the NASA ecosystem at all, right? So we allow more people to be able to use the sources that have been created, and this opens up our ability to accommodate people with different experiences and different perspectives that diversify that input to the scientific process, and brings more people to the table to use NASA observations. And then finally, NASA cyber infrastructure, or not NASA, sorry, open science cyber infrastructure must consider care and fair data principles. So I talked about FAIR a little bit. I feel like that's pretty well established in the community, and has been for a while. It's been around for about 7 or 8 years now, but CARE data principles have only been around since 2020. So, we're coming in on 3 years now. They're still pretty new. And it stands for collective benefit. So that's the idea that data provides collective benefit, that those who provide data have the authority to control that data. So you've seen that when you log into your social media and they now tell you, oh, we have new privacy policies, and you can go access your own data, and you can take your data down, and you can tell us what data we are allowed to have. This also goes to being respectful of those who have provided the data and not treating them as, cogs in the wheel, or just data sources, but they are human beings. And of course, being ethical and understanding that how what data you access and how you use that data has ethical implications for the people and the groups that may have been providing that data. And care data principles were originated for working with Indigenous communities. I think if you read these principles, they are generally good practices for thinking about working with any marginalized community, and honestly, just anybody, anybody who you respect. I think you would use care data principles. And the key point to saying that I think they're really essential for open science is saying that it's about serving communities independent of affiliation while respecting variable security concerns. So while we say open access, we want to have open access to everybody. There are certain groups who may have data or knowledge that they don't want to share, and they have very good reasons for not wanting to share that. And so we need to be respectful of why they have variable security constraints. We can talk about it in the context of Indigenous communities, but we can also talk about it in the context of, for example, the Department of Homeland Security, who may be trying to protect national security. And so access to federated services in a user's own environment, it respects these special requirements for data sovereignty or security. It also maintains the user's authority to control the data and the knowledge that they're creating and to decide when they're ready to share that. And it empowers each community to access and assess the inference of findings for themselves, rather than relying on processing by the limited few with the authority to operate within that intranet. And so, of course, as this evolves and as we learn and progress from the time that I give this conversation, I welcome people to come to the table and say, what? Services seemed like a good idea in theory, but since then we've learned X, Y, and Z, and we actually don't think that it's providing collective benefit. We have to be open to that conversation in a true open science cyber infrastructure world. Also, key findings relevant for open science cyber infrastructure is a need for a model of user deployed systems that plugs into paid services by the government for ease of use. And this really finds that balance of burden of cost between users and the service provider, like NASA. So when you think about this and you think about like sort of the traditional paradigm that we're in right now, still pretty heavy in to this day, users get allocations, let's say to NASA high performance computing or to NSF high performance computing. What this does is it limits access through a proposal process, which we all know is biased. It's inherently biased. And it's also constrained by funding and policy as to who can apply and how much means are available for that single agency to onboard you. The advantages to this is that it's generally cheaper to the user because a lot of that overhead is covered by the agency and they never see that. They just get allocations to run that are at a discounted rate. They also don't have to worry about security because it's all managed for them. In a service-based platform deployed by the user with predefined interfaces through core federated services, the limits of this is that it assumes equal capacity to pay, which we could accommodate through subsidies. So there are still certain groups who could pay for subsidies to that service, and that's what I'm going to show you on the next slide, or more expensive to the, and it could be more expensive to the user. So again, this is also without assuming any subsidy. Some advantages are standardized interface for the user, and it does not require affiliation access to the intranet, which removes funding and policy barriers. So one thing I want to highlight is that our biggest obstacle in open science cyber infrastructure is not technology. Our biggest obstacle is the cost models. It is overcoming the cost models and thinking through that. Here, what we found with ImgSPEC was a share the burden model, which is the federated services. We found that single source resource like NASA or NSF or university would benefit from this because it constrains their cost to operations, maintenance, and improvements to just that of the federated services, rather than producing every data product under the sun and then housing and storing that data product. It reduces the time spent onboarding users to centralized internet. It reduces costs of egress for users who don't actually know how to access data where it's located and feel that they have to move data around. It helps the user reduce the need to pay for big data storage. And it reduces time to learn new platforms, as well as time spent waiting for data to move around, which I don't have listed there. And subsidies and grants can be provided to support more equitable access based on economic means. I don't have the answer for how to do that, but it's certainly something we could look through. So I do want to just call out, and this is why I have Tyson here on the phone, that we are continuing development by integrating with Cyverse. And this focuses on the ease of deployment, this cost model issue that I've sort of drilled in, and security. And so the idea here is to continue to use the ImgSPEC extensions and the map code base to Jupyter Hubs and Eclipse Che to provide GUIs for auto scaling, but integrating with Cyverse's Cacao to enable users to deploy their own IDE via high performance computers, like through NSF, publicly or privately owned, as well as deployment on the commercial cloud. So what does this look like as a user story? You've got a user, they come in, maybe they have NSF allocations. As a minority serving institution, they have NSF allocations to CloudBank or to NSF Access CI, but maybe they don't. Maybe they just have a donor or a nonprofit or their own credit card. They want to just pay using their own money. They could also just directly access commercial cloud. And in any of these scenarios, they go into the marketplace and they launch their user preferred environment like RStudio Jupyter Lab. And it has all of these extensions. And when they launch that marketplace, they launch a Docker, and that Docker is being continually updated with the most recent federated services for executable fair jobs, metadata curation, API access, and then they also own their own data store and they're able to access and work with that. So finally, the last key finding for open science cyber infrastructure is a need for community of practice for contributing to any open source software. And what I mean by this is we need governance and documentation of processes and procedure for contributions as a system grows in functionality, reaching the limits of one project or funding source. So I mentioned, access for people who have certain senses and challenges with vision, let's say, or listening or audio or something like that. That may be outside, or let's say they don't speak English, they only speak Spanish. That may be outside of the scope of any one government or agency to provide as their service. But by creating a community of practice, we enable parallel development of added functionality by a broader community. And it's really important to note that ImgSPEC builds on the NASA MAP code base. And we worked with, many of the members of MAP were also with ImgSPEC. And so all of our updates got integrated back into MAP. But what happens when you have a project like Cyverse that isn't in the MAP, in the NASA ecosystem, and they're building additional functionality that could really benefit MAP code base, but they're not on the inside scoop? How do we decide when to accept their augmentations and added functionality? And so this is really this idea of creating the community rather than just creating a code base that everybody then forks and adapts to their own needs and never feeds back again to help everybody else out. And so this is really the idea that Open science cyber infrastructure must become more inclusive through iterative improvements constantly, right? Like what I'm saying today, what ImgSPEC does today is not what it should be in 1 or 2 or 3 years. It should grow and it should evolve and it should learn as we go through care data principles and we say, is this providing collective benefit? If not, how do we mitigate it? How do we build in adaptations to make sure that we are providing the most equitable, trustworthy product for the broader community? And this is also sort of recognizing outside the scope, funding and timeline of single projects. Also that open source is not nearly the practice of making your code available on GitHub via some open source license. It's about creating the governance for a community of practice so that anyone can contribute necessary adaptations that advance capability back to the core software base. It's about creating clear guidelines and incentives on how and when to converge and share improvements. And it's about creating a social model that supports both code developers and those contributing research projects or research objects to that code base, like an algorithm, for example. So I'm going to stop here. If you want, please screenshot this slide. If you take anything away from today, this would be what I would hope that you would take away, is that open science cyber infrastructure serves across the user experience community, security and affiliation gradients. It uses a model for user deployed systems that plugs into paid services. And it supports a community of practice for contributing to open source software. And with that, I will end with this quote that to truly accelerate scientific discovery and applications of Earth observations for using big data that help design a more resilient future, we need to democratize our ability to provide value-added data products and analytics, which necessitates reducing barriers in support of equitable access for big data and compute. And this is a quote from a paper that we currently have in review at Journal of Big Data. And with that, I will end and open it up for questions.
Thanks, Natasha. Fascinating and a huge amount of information. So thanks again for that. We will open it for questions. If you would like to take yourself off mute and ask questions, that's great. Or you can pop them in the chat and I will relay the questions. Well, I will dive in, Natasha. Thanks again. I was wondering if you could talk a little bit about kind of the user base that you engage with for the user acceptance tests. Kind of what those groups look like.
Yeah, so a lot of them were kind of the internal science team that we had. So that included professors, students, technicians at different universities. But then we also had like one, I think it was the 4th test, where we opened it up and we brought everybody from lots of different projects across NASA, as well as funded by NSF. We even had a few like managers sitting in, working with us. So the idea was kind of to try and we couldn't do that on every test. And that would be, I think, a little bit burdensome to the people who are providing feedback. But we did try to open up to as many people and receive comments from people as much as possible. I will admit that our biggest challenge was that, and this is the lesson that we came back, was the way that we had deployed ImgSPEC was we had done it as a project, and we had done it as a project at JPL. And then we had to onboard people in order to give them access to the system. So a lot of the user acceptance testing had to happen with one of our pre-approved people sitting there pointing, and like people couldn't get their hands dirty with it because we could not get past the security barrier. And so that's why I've integrated that as like such a key lesson, is that people have to be able to launch within and not have to be onboarded. And this is actually part of the value of the partnership with Cyverse, who has done this with a lot of, they've been so successful across the United States, launching their system for lots of different groups and having it be sort of a contained system. But we wanted to marry the capability of what Cyverse could do to launch that system, and then what we were thinking about through these like sort of services that think through all the interfaces for users and help them through that process. So that was sort of why that partnership and relationship with Cyverse seemed like a logical next step to build out the capability. And I don't know if Tyson wants to say anything to that.
I put into the notes the links to a couple of recent papers where Cyverse is being used to power this cloud infrastructure that we're calling Cacao. So the Cacao stands for Cloud Automation and Continuous Analysis Orchestration, but it's building that template below the ImgSPEC software to provision hardware. And so you can provision infrastructure as code and then deploy ImgSPEC on commercial cloud or on public research cloud like OpenStack, which is what's powering the Jetstream 2 platform. But those templates are, like Natasha was saying, it becomes reproducible, and you can now run that service anywhere. And anyone can run that once they learn how to use these templates.
Thanks, Tyson.
I'd be interested to hear from others who have been participating in the ESIP Open Science Cluster. You know, how does what you heard today from sort of the cyber infrastructure perspective resonate or contradict some of the other conversations and thoughts that you've been having in open science about open science?
Thanks, Natasha.
Hi, Natasha.
Hi.
Michelle Thornton. I'm at the one of the DACs, the data centers, the one in Oak Ridge. And what you say resonates very well with everything going on. And I recognize that you're trying to tie together a lot of pieces, which is admirable and needed, and I think will take time and support. The pieces that I see through OpenScape's collaborations and being a mentor with that and trying to develop help tutorials to help just kind of the basics of logging into the NASA cloud, and you need your Earth data login and you need your credentials and that and then, you know, do you download data? How do you combine data that you have with, you know, cloud-based data? It's a lot. It's a lot for users to get through. And, you know, to have that, you know, those services are key. And one thing that I see as a challenge that I think you're also addressing are, we have the DACs through individual development have a lot of API type access to data that a lot of users are leveraging and making really good use of. And so people are accessing NASA data without really knowing that they're accessing NASA data because it's in a crop model or it's in a phenology model or a hydrology model. So how do we not break that, right? How do we go to the cloud and have enterprise services and yet maintain that, you know, that takes away some of those barriers that you talked about in the beginning. It makes the data more equitable with outside people building those applications on top of the APIs that we have. So I think what you're doing addresses some of that.
Yeah, and I agree. Like, I'm not saying, hey, I've got the solution to all of this, right? You know, I'm just trying to I think the goal for me is to bring all these different pieces together and to get people to start seeing the nuances of each of these different elements and how they play together. Because it's going to take all of us, right? Like we say that about, you know, climate is changing. It's going to take all of us, all hands on deck, right? Well, you know, to create the tools that allow all hands on deck, it's going to take a lot of people. And that's why I sort of really put that community of practice as my last takeaway bullet of how essential it is to say, no one person, no one project's going to think about it. They're not going to come up with the silver bullet solution that's going to work. But we all have to figure out how to build on our capabilities and feed back to each other so that we're not duplicating effort and reinventing the wheel. We're continually making incremental progress towards something more inclusive and equitable.
Thanks for the question, Michelle. I think we have time for one last question in the chat. Venice asked, given the challenges of using containers for long-term reproducibility, did the ImgSPEC project reveal anything about other potential solutions for long-term reproducibility? And I apologize that I misspoke ImgSPEC and it should be ImgSPEC. So.
Oh, you're fine. Don't worry about it. Yeah, I can't, the short answer is no, we did not. But I do think Tyson has probably put some thought into that. And I don't know if Tyson, you want to add anything?
Yeah. So ImgSPEC is still ongoing, right? So NASA is still working on it. I'm still waiting for like the latest versions so I can try to reintegrate those into Cybers. So from the reproducibility perspective, you know, versioning of containers, trying to stay up to date as like we're seeing things like CPU architecture changing. So like we're running ARM processors on our laptops and not necessarily on our HPC centers yet. So I think there's always going to be the need for a human being on the loop to make sure that things are running. And it's something that we just can't leave alone. The software it's a living, breathing thing that needs people to help nurture it and keep it running.
And that's the value of a community. We keep everyone engaged. So I will say, I have a hard stop in 1 minute. So I put my email in the notes, and I would encourage, if anybody wants, they can reach out to me or Tyson, who's also left his email in the notes. And I just want to say thank you so much for the opportunity to come and share what we've learned along this journey.
Fantastic. Thanks ever so much, Natasha. Nice to meet you, Tyson. Really interesting webinar, and we will see the group next month, a week early, October the 17th, the third Tuesday of the month. Same time, same Zoom place. Thank you all. See you next time.